Hello. Yes, my name is Ryan Lopez. I work with Dr. Paul Atzberger in the UCSB Math Department, and we've been for over the past year researching how we can use VAEs for reduced order models of physical systems. So the method which we want to use is based on reduced order models. So a reduced order model would use time series data, um, high dimensional time series data, and try to find a good low dimensional representation of it, which contains the necessary information about the system. Now, this type of model is going to be good for dissipative systems because in dissipative systems, usually the higher frequency dynamics end up quickly kind of filtering out, and then really complicated initial conditions can end up turning into simpler solutions which are spanned by some low dimensions. So there are linear reduced order models. There are also nonlinear reduced order models, and they both have their own pros and cons. The pros of the linear ROMs is going to be that, well, one, they are better understood. They're usually simpler to implement, um, but they also suffer from, due to the fact that they are a linear approximation of the dynamics. Uh, they're they're not going to be able to perfectly model uh, nonlinear physical systems. Whereas on the other hand, nonlinear models, these will be able to, somewhat perfectly model nonlinear systems theoretically, but they're going to usually come with a number of problems with either stability or, it's difficult to train them or stuff like that. Um, So we suggest using VAEs as a possible nonlinear model for dynamical systems. Another thing which we do is we talk about how you can go about incorporating different latent space topologies in your reduced order model. Now, different latent space topologies might come up naturally depending upon the boundary conditions of your of the system that you're looking at. So you might have some system which is well described by two latent variables, but as you can see, here for the torus and for the Klein bottle, the boundary conditions end up making the latent space non-Euclidean. So we test both VAE as a non-linear reduced order model and these different topologies on both parametrized PDEs and mechanical systems as well. So to talk about VAEs as a dynamical system, first I'd like to start by just going over variational autoencoders. So the basic autoencoder will take some high dimensional input, and then there will be some encoder function, typically represented by a neural network, which will map the high dimensional input space data to some, low dimensional latent space data. And then the decoder will, map it back to the input space. And by training the autoencoder such that the output, well approximates the input, if it can do that, then the only way it could do that is if the latent space contains the information necessary to reconstruct the data. And variational autoencoders over here use a very similar idea, but are a bit more sophisticated because they use statistical inference. So instead of just taking a single input and encoding to a single latent space variable and then decoding to a single output function, now the encoder actually maps to a probability distribution in latent space, and the decoder will also map to a probability distribution into the output space. And typically these will have a neural network for the mean of the encoder and decoder, and a neural network for the variance of the encoder and the decoder. And in practice, this is done with, a sampler. We use Monte Carlo simulation. And some of the benefits of VAE is, well, since we're mapping to probability distributions, it's going to give some noise regularization. Since there's going to be some variance in where the input is exactly mapped to in the latent space, it's going to enforce smooth dependence of the latent variables on the input, and similarly a smooth dependence on the output of the decoder on the latent space. And VAEs also have an additional regularization, which is a prior in latent space. And this prior has been shown to promote disentangled latent variables. So, for example, in the bottom right corner over here, we can see a beta VAE, which is essentially a VAE with an additional parameter, beta, which can increase or decrease the regularization. And this beta VAE was trained on facial data, and one of the latent dimensions that it found ended up corresponding to azimuthal rotation. You can see if you go left to right, it basically rotates the face. And if you look at the other latent variables, which it found too, that they're in general pretty disentangled from one another. So what we suggest for modeling dynamical systems with VAEs can be seen on the left, where we would have some input function at some time, which will be high dimensional, and then we encode it into a low dimensional latent space, right, which will be simpler and should be smooth dependence upon the input. And then we can perform the time evolution in this low dimensional latent space. And then after we perform the time evolution, we decode it into whatever our prediction is. So this is the general framework, and we have an evolution map inside the latent space, and you can apply it an arbitrary number of times to evolve arbitrarily long into the future. So the specific loss function, which we use to train this VAE, mainly has three different components, as you can see in this line. So the first component, L subscript RE, basically is asking the model how well can it take an input, encode it, evolve it a single time step, and then decode it, and how well will it get the correct prediction? Is the prediction accurate after a single time step? And then the second term in it, which has this beta out in front, which you can use to weight how important this is in the loss function. This is going to just be an additional regularization on the encoder, basically trying to push the encoder into a unit Gaussian or a normal distribution in latent space. And this term has been found in the VAE paper to promote disentangled latent variables. And the third term here, which also has a coefficient gamma out in front which you can alter to determine how important this term is. This term will basically say how well can it encode an input and then immediately decode back to the original input. No time steps involved. Just how well can it encode and then decode back? How well are the encoder and decoder inverses of each other? So those three terms are what we are really trying to optimize here. So we tested our model on Berger's equation. Now, Berger's equation is a 1D nonlinear PDE shown right here. The time evolution, there will be this advective term right here, the negative UUX. And then there's also a dissipative term. We chose nu to be equal to 0.02. And one of the things that's nice about the Berger's PDE is that the solutions and its behavior are pretty well understood, particularly due to the fact that we have the Cole-Hop transformation. Now, this Cole-Hop transformation will take some input data and transform it into a function which obeys the heat equation, while U obeys Berger's PDE. So the Cole-Hop transformation essentially takes our nonlinear PDE and after some nonlinear transformation, turns it into a linear PDE. Furthermore, this Cole-Hop transformation actually gives us a analytic reduced order model that we can compare our methods to because, well, the Cole-Hop transformation will obey the heat equation. And one thing about the heat equation is high frequency Fourier modes are going to dissipate very quickly, and in fact, exponentially quickly, whereas the low frequency Fourier modes are really all that ends up staying. So this gives an analytic reduced order model of perform the Cole-Hop transformation, keep only the first couple of Fourier modes, and then perform the inverse Cole-Hop transformation. And then here you can see an example of this is keeping only the first two Fourier modes of this solution, and the prediction is pretty close to the target. So here we have some. I've showed some results of our VAE dynamical model compared to some other methods. So we consider initial conditions, which will be the initial conditions will be spanned by a single parameter alpha. And the formula for the initial condition is right here. And then additionally, these solutions will evolve forward in time. So all of the solutions, all of the training data that our model will ever encounter will always be spanned by two latent dimensions. The first dimension, being alpha, and the second being time. So we would hope that we can create a pretty good two-dimensional, reduced order model for this. And we can see the VAE method, which I've described, basically perfectly, near perfectly matches the prediction after a single time step. There are, similar results for multiple time steps. And then over here, I've compared it to some linear methods. So for example, dynamic mode decomposition, which is a pretty popular linear reduced order model. And we can see that, the DMD is very good in many applications, but, it's a linear model. So it won't be able to perfectly, model the nonlinear behavior. And, we can see this, in the reconstruction examples. And I also, to sort of drive the point home of how important the nonlinearity is, I also used a linear VAE where the encoder has to be linear, the latent map has to be linear, and then the decoder map has to be linear as well. And here it actually had some benefit over DMD, but still cannot perfectly get the correct prediction. Here on the right, I've graphed some of the errors of the analytic Cole-Hop method is in green. I used POD, DMD, linear VAE, and then all the way down here, there's the nonlinear VAE with two latent dimensions, which performs much better than the other models. I'd also like to comment, I forgot to say this earlier, but there is the question of, well, how do you choose the latent space? And in general, for dissipative models, we've found that we can get pretty good results if we just set the latent space evolution to be exponential decay, because if the model has some dissipative aspect, the solutions will all tend to kind of decay towards the center of the latent space, which you would assume is just a function of which is just 0. So here I've what's nice about VAE also is that we can plot what the latent space that it finds actually is, and that makes our model much more interpretable than maybe some other nonlinear models, which can tend to have a lot more complicated factors. So as I said, our solutions were always spanned by the initial condition parameter alpha and whatever the time t is. So we can see the encoder chose to represent the different alphas in the angular direction on the manifold, and then as you go downward, sort of exponential decay towards the center, those will correspond to more and more time steps. And this is with the gamma regularization, which means that this manifold is what happens if you also require that VAE can just reconstruct the output. You don't just put importance on a single time step going forward. You also require that it can that it can reconstruct data, which ends up making these two manifolds sort of overlap on top of each other. You can see these arrows when you apply a time step. The manifold just sort of decreases and perfectly fits over itself. Whereas when we set gamma equal to 0, and we only want the method to predict a single time step forward, then you see there's some kind of overlap, or then it doesn't perfectly match up, and this ends up having poor multiple time step accuracy. And then here on the right, there's just some extrapolation results of alpha outside of the training data set for VAE, linear VAE, DMD. You can see VAE is pretty good at extrapolating. So the next thing that I wanted to talk about was how we go about incorporating different latent space topologies. Now, it will often be the case that our data set might live in some manifold M, and due to the Whitney embedding theorem, we know that we can embed this manifold into some higher dimensional space. So to make our latent space the manifold, we basically first apply a neural network to the input data, which reduces from the high dimensional input data space into sort of the embedding space. And then after we've done that, we apply a projection map mapping from the embedding space, and we project onto the manifold. Now, all that we really require here is that we don't require a analytic function for for the projection map or for the manifold. All we really need is a point cloud representation of the manifold, and then our projection map can just be sort of like a nearest neighbor search, finding the nearest point on the manifold. Now, this seems like it might have a problem, because if we want to use this as our encoder, we have to be able to back propagate losses in our VAE. So we need to be able to take the gradient of our encoder, but we have a projection map here, which is just a nearest neighbor search. So we have to incorporate, our own analytic gradient, which the details of this are on the right here and are also in our paper as well. And this, this gives, this is better than, some other methods which have been used in the past with projection maps, because of the fact that all we need is really, all we need is a point cloud representation. We don't need an analytic projection map. And we do also need a coordinate chart on the manifold, but this is typically not that difficult to, this is typically not that difficult to get if you have a point cloud representation. There are methods of doing that. So here are some results applying these non-Euclidean latent spaces. So we considered both the torus and the Klein-Bottle example for not dynamics, solely for reconstruction. And we considered these constrained mechanics problems where we have, an arm here, which, has a joint x1 and the end of the arm x2. And if you have the position of both of these, that's going to be some data point in R4. But obviously, the system can be fully described by two variables, theta1 and theta2. But these are going to be periodic, so we can't just use a two-dimensional Euclidean space. We need to use a torus. And when we apply this method, we can see that the manifold actually performs better reconstruction than just two dimensions, because the two dimensions has to have some, it has to deal with the boundary conditions. And then there's also and then it also performs better than R4, just because, there's less room for, the VA. There's that you definitely suffer some consequences by using R4, because the latent space is inherently two-dimensional. And similarly, you suffer consequences if you use R10 as well. These are the L squared reconstruction errors for the arm mechanics problem for both the torus and Klein-Bottle. So that's it. Thank you guys for listening to my presentation.